Today we're going to talk about code optimization. Basically chapter 5 in the book. So we get to cover an entire chapter in one lecture. That should be fun. This is actually a topic that's near and dear to my heart because I teach the graduate level compiler optimization class in the spring. Obviously, we won't cover an entire semester's worth in this class, but I will use example that I used on the first day of that class, incorporated in this lecture as well. All right, so today we're going to give an overview, talk about some generally useful optimizations the compiler does. Then we're going to look at some things that prevent the compiler from doing a better job, the things to think about when you're programming. We're going to talk about exploiting instruction level parallelism. This is the notion that the processor can actually do more than just one instruction at a time if we sort of set things up properly. And then sort of a blocker of that is conditional expressions and how you deal with that. Okay, so again, why, we're not having you write compilers, write optimizers in this class, but we're trying to get you to be in a position where you can understand the performance bugs in your code. Okay, understand what the bottlenecks are and how to get around them. And so part of that is sort of understanding what the compiler, the optimizer in the compiler can do, will do for you automatically, and what would you hope it might do, but it doesn't do for whatever reasons. And again, you can adjust your code slightly to help it out, right? Ways you can help the compiler along. Okay, and we want to do all this improvements in performance without sort of destroying other nice properties of your programs, like their modularity and their generality. Okay, so we've seen some of the things that compilers do already, things like register allocation, but they also do they'll find redundancies in code and seek to eliminate it. Now, one of the reasons that we actually have you run GCC with basically almost no optimization whatsoever is so that you can see a more clear-cut mapping of the code you wrote and the assembly code. But in general, if you say do optimization level 3, it's free to pull things from all over the place, do inlining, all sorts of nice tricks that will speed up your code. All right, good. So code motion is a generally useful optimization. So this is one where you take some aspect of the assembly code that's done inside a loop, and you realize that it's loop invariant. That basically is not changing the value of this expression, the value of this thing that you're using is not changing inside the loop, so there's no reason to recalculate it every time you go through the loop. So here's an example here, kind of from the C code perspective, right? If every time you're doing this multiply to sort of get you to the proper row in the set row function, clearly that n times I is a multiplication that's happening inside your loop. If n is, say, not a power of 2, then you can't even do it using shifts, so you actually have to use an integer multiply. It can be an expensive operation. So instead, you just want to pull it out, right? So just pull it outside the loop. So that inside the loop, you're just referring to the result of that multiplication. Okay, so that's how you do it in C code. But as we'll see, the compiler will do that automatically. Okay, so here you can see that right here, you've computed ni times n minus 1, and it's basically outside. Well, let's see. Okay, so we go into this loop, we do this multiply, we compute this address, 0, right, and then we're going to just go inside the loop. So you can see that it's using the ni that's pulled out from inside the loop. Okay. And so that's, again, equivalent to having changed the C code as shown there. Okay, another thing that you've seen is the way it tries to take operations that are otherwise expensive, things like multiplying by powers of 2 and changing them into shifts, okay? Or these interesting calculations with the LEA instruction, right, where you can multiply something by 5 just based on the adjust calculations. Okay. Another thing that occurs a lot of time in code is a common sub-expression. So let's suppose that you have this sort of stencil-like program where you from a position I, j in your 2D stencil, in your 2D grid, you want to look at sort of what's one up. So if you're here in the grid, right, and it's some 2D grid, you want to look at the one that's up, down, left, and right of the point of interest. And so to do that, it's this series of address calculations, right? So to go up, you want to take the current, keep the j, but jump up by a row. Down is the opposite. You want to add a row, and left and right, you just want to subtract 1 or add 1 to the value of j. Okay. So if you do that, then what you end up with is these 3 different terms you're trying to compute. The I times n, I plus 1 times n, and the I minus 1 times n, which would be 3 multiplications. But because they're very closely related, you can do it with just 1 multiplication, right? If you compute the I times n up front, then the relationship between these 4 different positions is easily calculated as shown here, right? Whatever that position is, you just subtract n to get the up, you add n to get the down, you subtract 1 to get the left, and you add 1 to get the right. Okay? And so if you look at the code that gets generated, you'll see that that's the shortcut that's made, right? And you end up with just 1 multiplication. And again, because n could be anything, it's not necessarily a power of 2. This could be, not a cheap multiplication, right? It's an actual, say, 3-cycle multiplication. Okay? So questions on that? All right, good. So now let's look at this example that I like to use in my class in the spring. And so it's a simple bubble sort algorithm. Okay, you may have studied in an algorithms class, kind of a naive way to sort. It consists of 2 nested loops, all right, and a comparison of elements side by side. So basically what happens is the first time through the outer loop, you sort of bubble the largest element to the top of the list by doing a bunch of pairwise swaps. And then so that sets it, and then you go down 1 from there, and you bubble up the second to most expensive, second to most large element, and so forth, until you finally get done and the whole thing is sorted. All right. Now this is a little artificial, but it makes for more interesting example. I'm assuming here that the programmer was resistant to the the C notion that arrays start at 0, and so they wrote their program insisting that they wanted to keep their values in A1 through AN, right, as opposed to A0 through AN minus 1, and they're perfectly acceptable to do that. Maybe that helped them with conceptualizing later indexing into the array and so forth. All right, and so what that means is that the address for A sub j is computed, the starting address of A. And we're assuming that the elements are 4 bytes, but you have to subtract 1 off from the j, right? So you take this array that's from 1 to n, and for C, for allocation purposes, we actually shift it over to 0 to n minus 1. Okay, so and this is just a swap, right? So you just if they're in the wrong order in terms of largest to smallest, you just swap them. Okay. So inside the compiler, it's going to start off and it's going to take this code, the C code, and produce some sort of intermediate representation. Okay, so some sort of notion of the code that it's used to. This is not necessarily anything that ever gets exposed to you as a programmer, right? if you play around with any of these compilers like LLVM, you have to learn what its internal representation is, and then you can get very facile with it and start to understand this. This is just a pseudo internal representation, right? But you can see what's happened here is sort of a straightforward transliteration of this code, right? So we wanted to start by setting I equals n minus 1, so that's what we did. And then we need to do this test, right? And so we flip it. We say that, as we've seen in other classes, we say that instead of doing the while, we do the exception. So if I drops to less than 1, then we're done. So we're going to jump all the way to the end and we're done. All right? Otherwise, we're going to enter this inner loop. We're going to set j equal to 1 right there. And again, if j is greater than I, then you're going to be done with the inner loop and go to the next step of the outer loop, which is here, which again, you decrement I, and so forth. Okay? Then the rest is sort of setting up the value a sub j by the addressing mode and h sub j plus 1. And then once you have the value of those two things, you compare them. And if they're in the proper order, then you move on to the next j. Else, you just swap. So this is all the swapping. Literally, you're going to have a sub j, so you compute that, and put it in some temp, and then you compute a sub j plus 1, and then you do the first assignment and the second assignment, and then you're done. Okay, so it's just a mechanical translation of the code. Okay, and when we do that, you get 29 instructions in the outer loop. So 30 instructions in all, but we don't, this one executed once, so that's no big deal. So outer loop has 29 instructions, including that there are 25 in the inner loop. Okay? So that's sort of the starting place. All right, so the first thing we observe is that there's this interesting redundancy in address calculation, right? So we wanted to compute a sub j plus 1. So the first thing we said is, okay, what's j plus 1? And then we remembered, oh, but wait, our addressing mode is, the address of A plus 4 times j minus 1, right? So just literally, just a direct transliteration, we subtract 1 off that, and then we multiply by 4, and then we retrieve that address, okay? And so this is the initial code, but then the first thing the compiler realizes now is that, okay, I've taken something, I've added 1, and immediately subtracted 1. Okay, so that's kind of redundant. And similarly here, we've added 1 and subtracted 1. Okay, so here we've basically recomputed an address that we already have in some sense because we've already had to compute both these values. And again, here we add 1 and you subtract 1. All right, so the first step you can do is you can take all these 4 sequences and you can just locally decide that you can place them each with 1 instruction. Okay, so there's no more adding and subtracting 1 and so forth here. There's no more recomputing address because we already have it, and so forth. Okay, so how are we done? So now we're down to 20 in the outer loop and 16 in the inner loop. Right? It was, what was it before? It was 29 and 25. Okay. All right. So now we look and we see something like this, where again we were doing the swap. So we're sort of reusing these addresses, but the first time through, we're just blindly recomputing each address, right? So there's redundancy here. So we can take all this instruction here, which was just used to do the swap, and we can just replace it with these things, right? So let's back up a second. We already had a sub j hanging out in temporary 3, and a sub j plus 1 hanging out in temporary 7. So doing all this work to compute, to compute their addresses and retrieve their values is not needed. We can just use the temporaries that we have stored. Okay, so now we're down to 15 and 11. So good. another thing, again, I mentioned it looks closely at loops. So what's done inside a loop and what we avoid doing inside a loop. So if you recall in this loop, so this is the inner loop, we set j equal to 1, we do this test, and then we start this address calculation based on j, right? And then later we do j plus 1. Well, the interesting thing here is that because this address calculation is sort of going lockstep with incrementing of j, right? Every time you increment j, this address calculation ups by 4, okay? So there's actually no reason in this code to do both, okay? And since we need the 4 version of it for the rest of the code to work, we're just going to use that instead, okay? So now all references to j are gone, and instead we just initialize the starting points of j and j plus 1, and compare those, right, in this equivalent, right? I can compare 4 times j and 4 times I, just as easy as I compare I times j and I. And then instead of bumping up by 1, we bump these things up by 4, okay? And so that's, again, useful because now in this final code, we only have 9 in the inner loop as opposed to 11, and still 15 in the outer loop. So we basically cut things by, roughly about half for both the outer and the inner loops. All right, so any questions on that? Yes?
How do we reflect this change in C code, or is it only on machine level?
So this is inside the compiler. So what would happen is that when it was done doing all its optimizations in its intermediate representation, then it would have a instruction selection phase where it would then spit out the assembly code or spit out the machine code.
So they're all the same C code, but this is like optimization in the machine, like in the compiler.
Yes.
Okay.
Yeah. So it doesn't go back and fix your C code for you. Other questions on this? Okay, and you can imagine that there's a lot of analysis the compiler has to do to get this right? Because it has to make sure that things that you've defined in this little segment of code here aren't somehow used later, and so forth, right? Or a big part of the compiler is making sure that the transformations it does are safe, right? They're not going to mess up the code. Okay. So what are some of the limitations of optimizing compilers? Again, they have to be safe. So they have to take the information they know about your program and make transformations that don't break it. Okay. Now there's this one caveat, which is kind of fun. If you happen to write a program that uses some non-standard language feature or something, then the compiler is often allowed to do whatever, right? So why is that? It's basically because you don't want to force the compiler writer to have to accommodate all these non-standard features. And so it's going to just do whatever's convenient for programs that use the standard features. And if they happen to do some weird stuff for non-standard features, then so be it. Buyer beware. Okay. And the other thing is that, and we're going to talk about this in this class, there's like things where you look at your code and say, like, this is obvious. Why isn't the compiler figuring this out? Okay, and again, part of it is that there's information in the programmer's head or in other parts of the code that the compiler just doesn't see, right? That basically, you may define a variable that has a fairly wide range, but as a programmer, there's only some number of possible data values you're going to use in your program. And, so because that's in your head, you think, oh, the compiler should know that too, but it doesn't. Okay. The other thing is that compilers, I mean, there's a reason we have different optimization levels in compilers is because there's this trade-off. The longer the compiler spends running analysis on your program, then potentially the faster you can make it run. But there's diminishing returns, right? And so one common thing is separate compilation, right? So if I compile a file that's part of a larger program, C file is part of a larger program, the compiler may not have visibility to those other files, right? And even if it does, the analysis gets more and more expensive depending on how many pieces you bring in, right? If you have 10,000 lines of code and you're asking the compiler to do some analysis across 10,000 lines of code in order to do some optimization, that's, as you can imagine, incredibly expensive, right? Okay, and so typically most analysis is performed only within procedures. Okay, so you just locally look inside a procedure, because otherwise you have to figure out all the possible ways this procedure can be called and the relationship between all the arguments. There's all sorts of variations on this that people look at, but it's not, in general, it's considered too expensive, or would be too expensive to do sort of a full-blown interprocedural analysis where I decide how to optimize a particular function based on all the different ways it's called and all the different contexts it's called in. So traditionally, and the compiler you're used to using, it's all based on static information. It has the code that you're handing it. It doesn't know the inputs, for instance, right? And so because of that, it has to make conservative assumptions about what might the inputs be. Okay. Now, I qualified that a little bit because we have sort of just-in-time compilation techniques and so forth that will try to make use of information it learns about say the arguments to a procedure as things are running and re-optimize on the fly. But that's the standard approach, particularly for languages like C, is strictly based on static information. Right? It's what the code is on the page without executing anything. Okay, and again, when in doubt, the compiler must be conservative. Can't make things wrong. Okay, so this is an interesting example. So it's a simple thing. You're just trying to take a string and convert it to lowercase. Okay, so the basic operation is that if I have if I have a character that's basically in the capital A to capital Z range, then I want to convert it to lowercase a to lowercase z. And since the letters are at sort of the capital letters and the lowercase letters are at a fixed offset from one another, I can do this simple arithmetic. If I just subtract off the difference between the start of the two alphabets, then no matter what character I have, I'm going to jump it from uppercase to lowercase. Okay? And so the programmer says, okay, this is what I want to do. I want to go through my string for however long it is and do this simple conversion. All right? So you'd think, okay, I look at this, it's got to run through a string. It's going to take time that's basically the length of the string. Right? Some constant times the length of the string. But let's look what happens. Okay, when you run this, and this is time on the y-axis and the string length on the x-axis. So if it really were linear, you'd see a straight line here. Instead, we're seeing a quadratic curve. Okay. So why is that? Anybody have a guess? Yes.
Because it has to keep calculating the offset.
The offset. Well, it's just doing an increment each time to do the offset. So that's a sort of a constant operation each time to loop. Yeah.
It's calling Sterling for each loop of the string.
of the.
Right. So the thing is, it's this function call, right? And Sterling, what it does is it marches through the string until it sees null, and then it's how you know how long it is. Okay. All right. So so if you see how this code gets converted into sort of the go-to form that we talked about in the previous class, you'll see again that this Sterling is inside every iteration, and you know, it's calculated by you know, incrementing until you see that null character that delimitates the string. Okay, so that means that you know, it's called. It takes n time the first time through. Since you're shifting off the looking at less and less of the string each time, it's n minus 1, n minus 2 down to 1, but that's still a quadratic form. So if you sum those all up. Okay, so a very simple fix that you say, well, why can't the compiler figure this out? Is, you know, just pull that string-like calculation out of the loop itself, right? Do it up front, right here, and then we're fine, right? So then the code looks like that. Okay, you can't even see the slope, but it's basically it's linear in the length of the string. Okay, the lower 2 is the version where it's pulled out. Okay, so so why couldn't the compiler pull that out? Because it was a function, right? And it has to worry about you know, the various kinds of side effects that procedure Sterling might have, right? It could, right? It could depend on other things going on. Maybe the string is being updated behind the scenes every time. Maybe there's some other procedure that's actually, and we'll see an example of this in a minute, that's sort of later adjusting the string, right? So it doesn't know that Sterling is going to return the same value every time. And so that's why it has to be conserved. Okay. So because of some of these issues with procedure calls and some of the overheads of procedure calls, one of the things you can do for shorter procedures is the compiler can inline the procedure itself, right? And then therefore, because if it can see the entire contents of the procedure and knows that there's no way that anything else can mess it up, then it can actually realize that this value isn't changing, do the analysis, and go from there. And the other thing would be, of course, do your own code motion, which is what pulling the length out of the string was. Okay, so this is an interesting example. So here we have, we want to sum up the rows. We have a two-dimensional matrix. And we want to sum up the rows and store it in this vector B. So we pass it a pointer to the matrix and a pointer to the row we want to populate and the length. Okay? And so what it does is it goes through and it says, well, initially I'm going to look at one row at a time. And initially the sum of that row is going to be 0. So the ith row would be 0. And then I just run through the elements of that array and accumulate the sum. Okay, and then when I'm done with that row, I do the outer loop and I go to the next row and so forth. Okay. So if you look at what's going on here, this is the inner loop. You'll see that it's doing this floating point load and then an add and then a floating point store. Okay, so it's updating basically this B sub I every time through. Okay. So, but to think about how you're using that, you're just using that until the very end. It's just accumulator. You're just accumulating the sum as you go through. Okay, so so the programmer, as we'll see in a second, can actually do that. Can say, oh, well, let's not confuse the compiler. Let's actually create a temporary that we accumulate in, and then only at the very end do we store into memory what the output of that temporary is. But you look at this, you think, well, why can't the compiler figure this out? I mean, it's you know, it's what we're doing, right? It's this. You know, it's just an accumulation here. Why is it bothering to store it every time, and then the very next time through the loop, it loads it up back up again, right? It seems very wasteful. I mean, at the very least, maybe it's, if I've got it sitting in this register, why do I need to load it again? It's just there, right? Let me see what the issue is here. Why is the compiler actually correct in not doing these simple optimizations I just discussed? Yes?
It's because in the options this is running parallel with something else that the memory at that location might change.
That's, you're on the right track. We have two arguments here, a pointer to A and a pointer to B. Okay? What if those overlap? Okay? What if every time you update B, you're actually changing part of A? All right? And we have an example of that here. Okay? So let's suppose that, just a simple 3x3 matrix. Okay? And with these values, and we're just trying to sum these different rows. But then we happen to find B as being this, this slice of A. Okay? So initially B is what we'd expect. It's 4, 8, and 16. But now we start to run this code. And let's see what happens. Okay? The first thing that happens is we're going to set B sub I to 0. Okay? So that means that there's a 0 here. Which then, of course, means there's a 0 in the A version too, right? Because they're referring to the exact same addresses. So by doing this assignment of 0 here, I actually set that to 0 there. Okay. So now I start to do the sum. So I want to sum the first row. So I sum the 0. Okay, and I'm going to add that to the 0, and I get 0. And now I move to the next element, and I got a 1, and I want to add that to my running sum. So that's why this becomes a 1, because it's a 1 over here. Right, and then I'm going to add this 2, and it's going to be a 3 here, which is sort of what I expect, but then it's also a 3 there. Right? So this is correct. This is the sum. This B vector has the sum of the first row, as it's supposed to. But as a side effect, it's actually changed the contents of A. So now when we go on to the next row, this second row of A is interesting, right? It's changed, okay? And as we go through and we add up and so the first thing we do is we set this thing to 0, which we meant to do over here, but because of this aliasing, it actually also sets that to 0 there, right? And then we start to accumulate, so we add this 3, and then we add 3 to itself, and we have a 6, and now we add the 16, and we get a 22, okay? So it makes sense from the B perspective because 22 was the sort of the values in that row as we saw them, as we marched through them, but they were changing on the fly, right? I mean, it's no longer even the sum of this row, okay? So because this is possible, the compiler has to, dutifully store back the result in the BI and read it back out to see if it's changed, okay? Because in this case, it has changed. All right, any questions on that example? All right, and so forth. Just same thing, it continues on, okay. But now, if what we do is we just say we're just accumulating this temporary, so let's define a temporary, right, that has nothing to do with A or B, then now I can do the accumulation and then just sign it at the end, right? And I don't have to worry about this aliasing issue. Okay, and you can see from the inner loop, it's very simple. We're no longer doing a store and then a load, a store and a load, a store and a load every single time. Okay, so memory aliasing is when two different memory references, say in like C code, actually specify the same location, a single location. All right, a version of this would be if there's somehow overlapping locations, right? So if one reference, one memory reference is to a byte that's in the middle of a word of another memory reference, right? Then there's aliasing involved there, right? And because of that, the compiler gets blocked from doing various kinds of optimizations, even though in your head maybe you know you'd never be dumb enough to pass it the A and B argument that I just showed you before, right? So the way to get around it is to introduce these local variables like we did for this accumulator val, and just accumulate separately within loops and so forth. Okay, so questions on that? All right, then it's quiz time. All right, in the interest of time, we're going to move on ahead. You can do these more at your leisure later if you want to think about them some more. Okay, so the first question was a stack review question. People did pretty well on that. It's just capturing the notion that just because you move the stack pointer doesn't mean the thing that was there before has disappeared. It's still there. Right, so in this example, we pushed 15 to 13 onto the stack, and then we popped from the stack, but that just moved the stack pointer. It didn't actually erase any values. So you would still see that value on there. This second one is a variation on the uppercase to lowercase one that I had in class, which tries to avoid the Sterling altogether. Again, it's just a little bit of a review on your facility with manipulations of pointers and so forth. It turns out that's correct code. Nothing wrong with that code. And good. The last question, a little bit tricky as well. So what makes aliasing hard is not the case where the compiler can tell that they're always alias. Okay? It's really when it doesn't know. I mean, there are many cases in your program where the compiler knows full well that these two things refer to the same thing. And if it knows that, and it knows that, for instance, they always do, then it's able to act accordingly. It's not fooled at all, right? It knows that there's multiple ways to reference something off, relative to the stack pointer and so forth. So it's not that it's not that the aliasing itself is a problem. It's the uncertainty about the aliasing that's the problem, right? Because then the compiler has to be conservative and say, oh, I'm going to assume that these might alias when in fact, maybe they never do, and then I have to do something really conservative. Any questions on that? Yeah.
I actually have a question about the first one. What would an assembly code example look like that would cause a seg fault? If this isn't like unallocated memory defined as anything below RSP, so like from an assembly perspective, what would the seg fault look like?
So in this case, I don't know how, so the cases we've shown in class where you get seg faults is when you sort of access past, sort of legitimate regions of the stack or memory that you're allowed, right? So, we had that example where you created a buffer that was too small and you kind of wrote way past it, right? And then at some point, you wrote something that caused the system to crash, right? So it's like, so for instance, if you corrupted the return address on the stack, right? And then you try to branch that, you could go off somewhere. Yeah, but in general, I don't know necessarily how you would get a seg fault off just pushing and popping. Yes?
So for the second question, what if the input string does not have null character? Doesn't that mean that the string is not safe?
Well, if you give it a string with not a null character, then it's going to correctly just keep going until things crash, right?
Yeah, so like how is it a valid implementation?
Well, it's true of any of the string operations, right? That's how you get. C does not protect you against sort of passing in invalid arguments, right? So it's no different from the Sterling.
But don't we have a safer version of Sterling?
Yes, you can. Well, there's safer versions of all the string manipulation things. We actually specify lengths of things, so you don't go past the boundaries. But you don't have to use those. You can use the other ones and then, control. Okay, good. Good questions. All right.
Can I ask another question?
Yeah.
So on the first one, why is it not unknown? Because that place in memory is below where RSP is. Like, can't you not guarantee that your computer team will be there? Like, that's fine.
So what happens is that this is okay. So yeah, there's some assumptions here. I mean, it's just a quiz, right? Let's keep it simple. So this is sort of single-threaded code. There's only one thing going on. Okay, And so the state of the stack is as you left it, right? But you're right, if you had multi-threaded code and so forth, then other things could be happening, right? Good, yeah, and there's a balance to try to keep quiz questions, it's the same over here, right? Balance, keep them simple and yet not worry about all the corner cases. All right, good. So let's get back. Okay, so let's talk about instruction level parallelism. Okay. So I'm going to jump to right away. All right, so this is sort of the modern CPU design under the covers, right? You've got a cache which is holding recent instructions and sort of speculating a little bit to fetch more instructions. From that instruction cache, you have sort of a stream of instructions being fed into the code. That the code is determining right, so for each instruction that gets decoded, there's going to be some values, some registers you're going to need, and there's going to be some, potentially, unless it's just like a move, there's going to be some operations, register, move, there's going to be some operations that are being performed, right? And so, but there's sort of a pipelining that's going on, right? So you decode an instruction and you fire it off to, say do an add or something, the next instruction is being decoded and so forth, right? So there's this whole pipeline of things, this whole collection of things that could be happening in parallel. And the limits, there's a number of limits to this parallelism, and one of them is how many of these functional units you have and what type are they. Okay, so in this diagram here, we're showing an architecture processor where you have one load unit and one store unit and 3 arithmetic units and a branch unit. Okay, and so what that means is that there's an opportunity here to do 3 arithmetic operations at the same time and as one another, as well as at the same time you're firing off a load to memory and a store to memory. Okay, and trying to figure out some sort of branch. So there's this parallelism hidden inside these machines that you're trying to take advantage of. Okay, so let's go back. Okay, so certainly the compiler itself needs to understand the number of function units and the restrictions on the function units on the processor it's running on. And so, and then do optimizations accordingly. But also, as a user, you could be thinking about what's going to speed up your code based on knowing what things can happen at once. Okay, and again, there are cases where, if the compiler can do it for you, that's fabulous. You don't have to worry about it. It's actually more portable because the compiler can, recompile for different architectures and so forth. But if you're in one of these optimization blocker settings where there's something about your code that's preventing the compiler from figuring it out, then you can often help by doing simple transformations to your code. And we'll see a running example here. Okay, so let's suppose that we have this sort of a generic data structure for vectors that exists of a length and the data itself. So here's what it looks like. And you want to use it to hold, integer vectors and longs and floats and doubles, right? And now you have another function that's going to take as an argument one of these vectors and then an index into that vector, and it's going to store into this the value of that vector at that index into this location. Okay. So again, if you give it an index that's too high, it's going to return 0. Otherwise, it's going to return 1, and the value at that position is put into that location for you. Okay. So given that we have that, so that's called get vector element. Okay. So we have this type, and we have get vector element. Now we have this combine operation, which you want to use as sort of a generic way to compute both either a sum or a product of vectors of any of these different types. Okay? So in order to do that, what you do is you have sort of an identity, right? So for instance, if the operation I'm passing is a plus, the identity is 0, right? You start from 0 when you're accumulating adding. On the other hand, if the operation is a times, then I'm going to start from 1, right? Because then 1 times blah, blah, blah. It all works out. All right, and then I just run through the elements. I get each element one at a time, and then I add it into this running accumulation of either the sum or the product. Okay? And when I'm done, the actual thing is in the right place. So now we're going to run this, and we're going to account for the number of cycles that it takes to perform. So I have this notion of a CPU, cycles per element. For each element of the vector, each operation we're going to perform, we want to know how many cycles it is. And then the time is just the how much time you're spending per element times the number of elements plus some fixed overheads for starting and stop and wrapping up. And so another way to think about that is that the CPU is the slope of the line. So here, if I'm spending 9 operations per element, then the slope is going to be 9. But if on the other hand I only spend 6, the slope is going to be 6, right? And the x-axis here is the number of elements in the vector. So just changing the end. All right, so let's see how it does. So again, this is our code. And now we look at the 4 different data types. We have integer, or four of the possible data, two possible data types in both operations. So we have the integers and the double precision floating point. And we do both the add and the multiply in each case. Okay. If we just do this, if we just time this procedure on optimize, then the cycles per element are in the 20s range, right? If we run optimization level 1, then they cut in half. And if we run optimization level 3, then they sort of cut in somewhat in half again. Okay. So the types of optimizations are some of the ones we've seen before, right? So we don't want to store every time through the loop. So we want to use a temporary to accumulate, as we did in our earlier example, right? Earlier in the class. All right. And so anything else in the length, again, we want to pull that out once and for all, and not have to recalculate that. Okay. And sort of the address calculation, well, what we care about is where does that vector start, and then we're just able to do calculations that are offsets of that. Okay. So it moves things out of the loop you don't need, and it avoids sort of the bounds check on every single cycle, and it does the accumulate and temporary. So if we do that, and we compare that to, say, that just the opposite of 1 that we had before, then you can see that it's significantly faster, right? And it's even faster than the optimization level 3 of the old procedure. Okay. All right, so I already showed you that. So again, this whole use of this parallelism, the instruction level parallelism, is in this case mostly hidden from the C programmer. But if you know about it, then you can sort of set up your code to help the compiler take use of it. Okay, so continuing along this same example, the other thing that happens is pipelining. Okay, I mentioned there was sort of pipelining of decoding instructions, executing instructions, and so forth. But if you have an expensive operation like an integer multiply or a floating point multiply, and it's going to take some number of cycles to get it through, then again, that's broken up into itself a pipeline, okay, of say various stages. And then if you have something like this code here where you're multiplying A times B and A times C, then you can get A times B into stage 1 of your multiplier, And then when it moves on to stage 2, you actually can start up A times C, right? And so forth. So these two things can happen lockstep. If you had A times D, you could have started here, and you could get this nice, perfect pipeline, right? So while the latency of a multiplication would still be three cycles, because of the 3 stages, the throughput could be 1, right? Because you'd be starting a new multiplication every single cycle. Now here's an example, though, where we stalled and we couldn't start that till cycle 5. So why was that? Yes? Right. Yep. This is the result of this one, and this is the result of this one, okay? So the compiler has to take the into account as well, okay? It has to determine where these dependencies are, and it can't start scheduling an operation until the things it depends on are also complete. So in particular, the Haswell CPU has 8 functional units, 2 loads, 1 store, 4 integer, 2 floating point multiply, 1 floating point add, and 1 floating point divide. Okay. And it has this latencies. So for instance, a load or store could take 4, integer multiply 3 as we've seen. But because you could pipeline those integer multiplies as we've seen, the throughput is actually 1. Okay, the cycles per issue is actually 1. So if you have 3 integer multiplies you could do at the same time, then in a continued pipeline fashion, then there's no sort of loss in performance. Okay, and same things with loads, for instance, right? So even though it might take you 4 cycles to load something from the cache, the hardware is equipped with a way to sort of queue up these loads and pipeline it all through, so you actually return a load. If you have 4 independent loads, you can get them back in 3 cycles. The 4 cycles get the first one, but then the ones after that come 5th, 6th, 7th cycle after that. Right. So again, the sort of throughput is very good. And then you have things like integer or long divide, basically the divides that are just costly. They're not pipelinable; they're just costly. Okay. So unless unless you can get away with shifts by powers of 2 to do your division, it tends to be very expensive. Okay, so getting back to our combined 4, what we see here is that we had these numbers here from the previous slide. And if you just look at the latency bound, you see we're actually doing very well in terms of the multiply, add, and integer multiply, but not quite so well in terms of integer add. Okay. And one of the issues here is that the way we're accumulating, right? So remember, we're in each of these, whether it's add or whatever, we're one by one sort of accumulating in the next element in the vector. Okay. And so this is a whole bunch of serial dependencies. And that's why we don't see this pipelining, right? We're saying, oh, it's like the case of that third instruction we had to wait for, right? So because we have to wait, because this is one of the inputs here, it's one of the inputs to this multiply, we have to wait for this to finish. Okay? But, if this is a sort of integer, for instance, we know that multiplication is associative, so we don't have to do it this way. Right? So in particular, if we do what's called loop unrolling, where you step through a loop, not 1 at a time, but 2 at a time, and of course if it ends up being an odd number, you have to do that last odd case here. So that's what that is. If limit is an odd number, then you have to do the one last case, or length odd number. But in general, you'll be doing 2 at a time. Now, and so what you're going to do is you're going to accumulate the first one and the second one. So that's not that much helpful because you still have this serial dependency, right? And if you look at it, it didn't really help at all. It helped in the add, okay? You got down from 1.27 to 1.01, but you're still serializing, okay? So the trick here is to just associate it the other way, right? Okay, so now I can start to compute, this value without having to. I can start. So here I had this operation dependent on waiting for this to finish. Here I can do this operation first and then accumulate the result. So when I do that, and I realize I have these extra functional units, then my latency hasn't improved, but now if I look at my throughput, like how many of these I'm getting cranked through at a time, it's better, right? So it's gone from 5 to 2.5. Okay, so it's cut it in half. Okay, because I have these two functional units, I'm able to run them both in parallel, and I get that. Now, the goal would be this green stuff here, right? Because that would say, let's see how many function units I have, and if I can keep them all cranked up full steam, then I could achieve this bound here. So we're still pretty far from that, right? We're factor 5 here, 1.5, and 2 here, okay? Yeah, so this is just showing how you've reduced the serial dependencies so that there's only n over 2 of them. The length of this longest chain is over n over 2, and so that cuts it down. All right. So the next trick is to, instead of trying to accumulate into this one running sum, okay, since we're sort of, let's accumulate all the odd ones and accumulate all the even ones separately. Okay, so that's what this is doing here. So this is sort of the one has the even ones and one has the odd ones. Okay, and their own little temperatures. And then only at the end do we multiply the accumulated result of the odd versus the accumulated result of the end of the even. So the answer ends up being exactly the same. But when we do that, we see that there's some further advantage that we got in the add, but not the other ones. Okay, and it's because the add has, the integer plus is able to make use of the 2 load units. Okay. So what can we do now? So in general, you have this trade-off space, right? So you can do, you can unroll the loop to any degree L. We were just unrolling it 2, right? I could do unroll 3 or 4 or whatever. And you can also accumulate some number of results in parallel. And if you do that, then you see interesting things like this, that there's basically some sweet spots. So if you look at floating point multiply, you see unrolling by 10 and accumulating 10 leads to the fastest result. Okay, so up here, we're looking at this number, 2 and 2, and you can do better by in this case, choosing 10 and 10. Okay, so there's no reason to know, maybe offhand, without staring a lot at the architecture, which would be the best, but you could certainly try out different combinations in your code and see what works the best. Any questions on that? Okay, integer addition is a slightly different choice. It's 8 and 8 is the optimal. Okay, and you can see that in the end, when we do this, we're actually very darn close to the throughput optimum in all cases. Right. So we've managed to milk out of the machine all the performance that was there to be obtained. And again, these were limited. These two numbers are derived basically by the property, the function units you have and the properties of them. Okay. And this was up to 42x improvement over the original code. Okay, so any questions on that? All right. So in a previous class, we talked about these longer registers that we have for doing SIMD instructions. Okay. So the earlier versions were they're the XMM registers. These are the YMM registers. They're with the more recent versions of the Intel architecture. There are 16 of them total. They each have 32 bytes. They're 32 bytes long. Now, if you remember, the thing we said about them is that you can either you can treat them as a bunch of smaller registers and then apply sort of data parallel vector kind of operations on them. Okay, so you can, for instance, view them as consisting of 8 32-bit integers. And then if I apply one of these SIMD operations on them, I can do 8 things in parallel. Okay, or I can do 8 single precision floats. I can do 8 things in parallel. Or if I want double precision, I can do up to 4 in parallel and so forth. Okay, and so the SIMD operations again work just within each of the segments, and the way so the suffix of the instruction indicates which version you're using. Are you thinking these as 8 32 things or 16 byte things, 16-bit things and so forth? Okay, good. So again, we're not going to deal with the SIMD instructions in this class, but just to let you know that it allows you to beat things like this throughput bound, right? Because now it's still a single multiplier, whatever, but it's now across a whole bunch of these things at once in the SIMD instructions, and so the actual bound you can get is even better, right? But you can get a throughput bound of another factor of 8 here, because I can do this operations on 8 integers at once using these SIMD registers, right? So there's all sorts of tricks that can be played. Questions on that? Okay, so the last topic is about branches. So in order to get all this parallelism and keep all these pipelines full and so forth, the instruction decode needs to sort of run ahead of what everything else is doing, right? And so you want to be speculating on what instructions are going to be executed by the program well in advance of when you actually execute them, so you can start to fill all these pipelines. So the problem is conditional branches, right? So when I get to a branch and I'm not sure which path it's going to take, then I don't know where to keep fetching. I mean, like in this one here, I have 2 choices. One is I can assume the branch won't be taken, and then I can just start fetching all these guys, or I can assume it will be taken, and I can fetch from here, right? And again, the point is I'm trying to make this decision long before this instruction is even executed, right? So I don't know which way that branch is going to go. Okay. All right, so we've seen that already. Let me show you that. So there's sort of always going to be sort of the branch not taken path and the branch taken path. So what do processors do? Well, they try to predict, okay? And they have some rules of thumb for how they predict. And if they get it wrong, then they have to have the ability to squash all the computation that's in flight that they got wrong, okay? And then roll back and start again, right, from that point. So it doesn't lead to incorrectness, because the processors build all this additional hardware circuitry in it to handle the speculation of the state and the squashing of the state and the rollback and so forth. But the program slows up, because instead of having this nice stream of things you're doing because you're running way ahead, you not only wasted all this work, now you've got to jump back and cold start this whole pipeline again. So it's very noticeably painful in the performance that it takes. So a good example is always a loop, okay? Or can be a loop. So here, if you think about it, if I have a loop, then if I loop through something, n times, and then I drop out of the loop, if I always predict that I'm going to loop back, I'm going to be right, all but one time. Right? So that's what they do. Okay. So by predicting that a loop will always continue to execute, then you're only wrong once, which is good. And so this is an example where you're showing, okay, you're correct, and eventually you're going to be wrong. And you're going to have to squash, invalidate all that code and squash its effects and restart. Okay? Any questions on branches and branch rejects? So that's loops, like if, then else kinds of things. In general, it's hairy. The processor has tables inside it where it tries to keep track. They're called branch prediction tables, where it tries to keep track of, for every single place in the code where there's a branch, what was the most common thing it did, did it branch or not, and then use those to predict. So it kind of learns as the program is executing how things are what's the better choice, the if, the if then, the then or the else branch. And so as a result, you get at least 95% accuracy in these things. So that's good, but you will see the hiccups if you have code that doesn't allow for good branch prediction. In particular, in combination with these big, wide SIMD instructions, so you're actually wasting a lot of work when you have a hiccup. Yes?
So are there ways to explicitly structure the C code to make it more predictable? Or
well, so this gives you a clue. So before the default that will be assumed before the processor has any history of this branch is that right? So is when you have an if, then you predict that you don't take it, that you actually fall through, right? So if is often like, if the pointer is null, I'm going to do something else. The normal case is if the pointer not null, it's going to fall through. So if you have a choice of deciding whether to say, if pointer is null, then do this, else do that, or saying if pointer is not null, then you can help the system by making sure that the common case is the fall through and not the branch taken. Good. Okay, so sort of to summarize, you want to watch out for these hidden algorithmic inefficiencies that, like the Stirling, which is doing this calculation, this n-squared calculation when you didn't think about it, doing that. You want to watch out for optimization blockers, try to do things that are going to help the compiler, like use temporaries so they don't have to worry about aliasing. We spent a lot of time optimizing this innermost loop of this function. That's where most of the work is done, so that's where a lot of the effort is often spent. What else? Yeah, instruction level parallelism, knowing the number of functions. Again, the compiler will try to do this for you, but if you do things that aren't compiler friendly, you may get stuck. And and we'll talk later about writing code that's CPU cache friendly, so you get more cache hits. Okay, and that's basically today's lecture.